understand what I mean by the epistemological issues that stoichiometry errors expose, I first need to give you some background. I'll begin with some prior findings of mine related to work which I had published in articles in these journals, in particular a 2021 publication in Chemistry, Education, Research and Practice about South African physical sciences teachers' use of formulae and proportion in stoichiometry. I found that the teachers inconsistently recognized the need to use proportion in these 4 calculation questions. In this graph, the orange bars show how many teachers did not use proportion at all. Here are some examples to explain what I mean. This first teacher used the ratio given by the balanced equation. The second teacher used various formulae and algebraic manipulations, but no use of the mole ratio. They failed to recognize the need to use proportion across the reaction equation. The fact that I found that the recognition of the need to use proportion was inconsistently applied across the questions seemed more consistent with a knowledge in pieces rather than a knowledge as theory perspective. What do I mean by that? According to the knowledge as theory, conceptual learning is revolutionary. It happens when misconceptions are corrected. Knowledge, including errors, misconceptions, is theory-like, and so errors tend to be rather consistently applied. But according to the knowledge in pieces theory, conceptual learning is evolutionary. It happens as fragments of knowledge are joined and metacognition is improved to enable intuitive ideas to be suppressed as needed. Knowledge, including errors, is fragmented, and so errors are inconsistently applied. In the study I'm reporting here, I drew on data I collected at the same time as for the studies that I've just referred to. These were my research questions. I wanted to know what factors may have triggered that differential recognition of the need to use proportion. Which other calculation errors could the data allow me to examine for consistency? How consistent did the teachers apply these errors, and how consistently are these calculation errors related to associated conceptual errors? The reason why I wanted to investigate all of this was because I wanted to know which of these epistemological theories best describes what I observed. And the reason why that's valuable is because your epistemological view affects the way you teach. If you hold a theory view, you're going to try to expose misconceptions and create dissonance to bring about conceptual change. And that's the view that I had when I ran the intervention related to this study. Whereas, if you hold a knowledge in pieces view, you're not going to assume that every error you see necessarily indicates the presence of a misconception. You're going to allow for the possibility that a superficial question feature may have triggered the error, despite the person possessing the knowledge to answer correctly, if they would just be helped to retrieve that fragment of knowledge from their store of knowledge for that question. This is some of the information about the sample of South African physical sciences teachers that I used. I ran 8 two-day workshops throughout the Free State Province. I started and ended the workshops with pre- and post-tests, respectively. These had both conceptual and calculation questions. In this study, I'm focusing on the calculation questions, although I do draw on the conceptual question data to answer the final research question. During the intervention, I taught interactively for about 1-hour periods, interspersed with the participants working through an accompanying fill-in workbook, individually or in small groups, for 1 hour before we repeated the process. I presented the mole concept and proportion and taught the teachers to use the unit factor method. Since I'll refer to the unit factor method quite frequently, let me briefly clarify what I mean. Here you can see a question from an old examination. Here is the standard memo. Here's the use of the unit factor method, which is a generic proportion method which requires no use of formulae. These are the calculation questions for the pre and post tests. You can see that they're not identical, although they are very similar. This is an analysis of the question features using the frameworks given in these two publications. I coded each person's solutions to these 4 calculation questions in each of the pre and post tests in 2 ways. Quantitatively, with marks out of 16 for each test according to these guidelines, and qualitatively according to these categories of codes. This is how I analyzed the data relevant to answering each of the 4 questions. You can see that I used both quantitative and qualitative analysis. I'm going to give a bit more detail about how I evaluated the error consistency now. I'll just take one of the types of errors with coefficients, as an example as I do so. I defined each of these categories regarding the consistency of the error. Then I ran queries in the data to identify the numbers of people who fell into each of these categories for each of the pre and post tests, which isn't shown here. I'll get to that in the findings. But also for consistency across the pre and post tests, which is shown here. For categories of particular interest, I used these queries to direct me to the particular individuals who fell into that category, according to my codes, so that I could then return to those people's scripts and conduct a more in-depth analysis of their work. Now let's look at the findings. First, to answer the question about factors which triggered differential recognition of the need to use proportion, I generated a number of hypotheses, each potentially supported by literature. Remember that I'd found much lower recognition of the need to use proportion for questions 19 and 20 than for questions 18 and 21. And questions 19 and 20 are more complex. Also, the ones where proportion were used to a greater extent, 18 and 21, both had the word produced, whereas 19 and 20 did not. Here we can see the same trend that the previous graph showed in the pretest in the front set of columns. The middle set shows that almost all the participants recognized the need to use proportion in the post-test, with a bit of a dip for the percent yield question. The last set of columns shows how many participants used the unit factor method for each question in the post-test, and that's high but somewhat inconsistent across the questions. So in answer to the first research question, it seems that a more complex question is more likely to fail to trigger the need to use proportion, and the word produced might help trigger the need to use proportion. And an intervention which focuses on proportion through use of the unit factor method can be effective in making people aware of the need to use proportion. That might be because the unit factor method itself triggers an awareness of the need to use proportion because it's a generic proportion method. Next, I wanted to look at other calculation errors and how consistent they were within each of the tests and between the pre and the post tests. Here are errors that I identified which are related to ratio and proportion. The pre-test consistency is plotted in the columns and the post-test in the area graph behind the columns. As I've already discussed, there was a high degree of inconsistency in the failure to recognize the need to use proportion in the pre-test, whereas in the post-test, this error had largely disappeared. However, a fair number of participants did still display this error inconsistently. Nobody displayed this error consistently in the post-test, whereas a few participants had displayed this consistently in the pre-test. We see that the prevalence of the other errors is considerably lower than for the failure to recognize the need to use proportion. Also, there's more evidence for inconsistency indicated by the lighter pink or purple colors than for consistency indicated by the brighter pink or red colors, especially in the post-test. For these two kinds of errors, there was only one of the 4 questions per test which tested the error. So from the data I have, I can't examine error consistency within a test. I can only examine error consistency across the intervention, which obviously raises the question of how validly that demonstrates epistemology. Consistency here refers to resistance to change by the intervention. Both theories would allow for change across an intervention, although this would be less likely, according to the theory, since it views knowledge as more stable than the knowledge in pieces theory does. We see that errors related to the subscript of a molecular formula showed a high degree of consistency, resistance to the intervention. This graph shows the 4 types of errors observed during use of the unit factor method across the 4 questions of the post-test. Again, the main impression one gets is that there's more evidence for inconsistency than for consistency of errors. As I explained in the methods section, I ran queries to find individuals of interest, and then I drew out and re-examined these individuals' written work. I'm going to briefly show you one example that was identified as being of interest in this way. According to the query, this person consistently showed errors with coefficients in the pretest, but this error was absent in the post-test. As you'll see, though, a deeper qualitative examination actually revealed inconsistency. And the reason for this discrepancy is a lack of precision in the coding. So although each relevant question in the pretest showed evidence of errors with coefficients, the way in which these errors manifested differed, and there were instances of the correct use of coefficients as well. This is some information about this particular teacher. It's interesting to notice that although they made enormous progress in the calculation section of the test from pre to post, which we'll see in a moment, they made little progress in the subsection of the conceptual part of the test, which had to do with ratios and stoichiometric equivalent values. In the pretest, this person used proportion in a faulty manner in 2 of the questions and failed to use it in the other 2. In the post-test, this teacher used the unit factor method correctly throughout, even though to do so they needed to compile correct equivalent values from the mole ratio and the mole concept. That suggests an inconsistency between their conceptual understanding and their ability to perform a correct procedure. And we examine that more when we answer the final research question. Here we see question 18 in the pre and post tests, with the marks, codes, and more detailed qualitative analysis regarding consistency. Let's look in more detail at the pre-test answer. We can see that this person first presumably adds the 2 given amounts, 17 grams N2, although first they write this as 7 grams, and 0.5 moles H2. They correctly convert 0.5 moles H2 to 1 grams H2. So we can see that they are disregarding the effect of the limiting reagent by wanting to add the given amounts together to find how much product is formed. But then they make this even worse by changing this to addition of these given amounts multiplied by their substance's coefficients from the balanced equation. So that shows a faulty use of proportion using the mole ratio in the balanced equation. Then they converted their answer, mass of ammonia, to moles in a faulty manner by using ammonia's molar mass, capital M, which is 17 grams per mole, multiplied by ammonia's coefficient in the balanced equation 2, giving 34 grams per mole as ammonia's molar mass. So even just within this one question, we can see coefficient error inconsistency because they converted 0.5 mole H2 correctly to 1 gram H2, but they converted 20 grams ammonia incorrectly to moles of ammonia through application of the molar mass equals molar mass times coefficient error. I'm not going to dwell on the next question for the sake of time, but I just want to quickly point something out that's relevant to the methodology here. You can see that for the pre-test, the person didn't make any use of the coefficients, but that was probably because they failed to recognize the need to use proportion across the equation, in other words, to use the mole ratio. As I worked with the data, I realized this connectedness of errors. And so for the consistency analysis of the coefficient error, for each person, I only included questions for which the mole ratio was used. So for this particular person, this question was excluded for the pretest when making the judgment about whether they displayed this error consistently or not. In this question, we have the same kinds of errors as we saw in the first question. two kinds of coefficient errors. With hydrogen, we have the number of moles calculated correctly first, but then later the error of multiplying that by hydrogen's coefficient. And then with ammonia, we have the molar mass again calculated as molar mass, 17 times coefficient 2. So between questions 18 and 20, a particular coefficient error is consistently applied to hydrogen and a different coefficient error is consistently applied to ammonia, but the two types of errors are inconsistent between hydrogen and ammonia. This is the last question. This was the only question for which this person made a mistake in the post-test, and that was because they'd given the wrong balanced equation. Interestingly, they managed to give that same equation correctly in the pretest, which is another example of inconsistency. In the pretest for this question, they again displayed errors with the coefficients, but in a different way to all the other questions. So let's look at this in more detail. The S is to O2 ratio is incorrectly given as 2:6 instead of 2:3. The 6 probably comes from the coefficient multiplied by the subscript, and that's the first time we've seen such an error in all the questions. Then this ratio is used to calculate the number of moles of sulfur which reacts with 1,9 moles of oxygen, although there's an incorrect calculation in the last step. Then, that incorrectly calculated amount of sulfur is added to the given amount of oxygen to give the product's, SO3's, number of moles. Then that answer is incorrectly converted to grams by substituting a variety of inconsistent values into the formula small m equals n times capital M. N of O2 present, capital M as the incorrectly calculated N of S to supposedly reveal small m of SO3. Notice the capital M value isn't multiplied by SO3's coefficient here, 2, as for ammonia in the other two questions, nor is the final answer multiplied by the coefficient as for hydrogen in the other two questions. So in answer to the research question about calculation errors, these are the errors that I found in my data. And regarding the research question about error consistency, there seems to be more evidence for error inconsistency than for consistency, with a possible exception of the incorrect use of subscripts. Then what about the relationship between the calculations and the conceptual questions? I performed t-tests and correlation analyses to investigate this, as shown here. For the limiting reagent question, in the section in which the subscript of hydrogen had to be attended to, we can see statistically significant differences in the score obtained for the relevant calculation question between those who answered the conceptual item correctly and those that didn't. For the errors related to ratio and proportion, I found moderate correlations between the corresponding calculation and conceptual items. So what can that tell us about epistemology? If knowledge is completely theory-like, and if there were no limitations arising from the testing instruments and processes, we would ideally find a perfect correlation between performance in conceptual and calculation questions which test the same kind of knowledge in these different contexts. However, since the testing instruments and processes cannot be ideal, and there was not perfect equivalence of the conceptual and calculation questions, whatever that would mean, it's not possible from these findings to make strong claims about what this shows about the epistemology of knowledge. So, in conclusion, here are the answers to the 4 research questions repeated. I've already explicitly reflected on what the last finding seems to say about epistemology. In other words, it's inconclusive. What about the other findings? Except for the findings regarding subscripts, which should not be taken too strongly due to limitations in the data, it appears that there's more evidence for inconsistency of errors in the data available than for consistency. This study has certainly personally thrown enough doubt on the knowledge as theory for me and made me more aware of the knowledge in pieces theory to change my own pedagogy. Although I still think there is a place for exposure of misconceptions and attempts to create dissonance, I will not stress this as much and devote as much time and energy to this in the future as I did in the past. Instead, I'll give more credibility to the possibility that a person who displays an error might actually know something about answering that type of question, but perhaps surface features of the question might have thrown them off. I'll assign more value to using the fragments of correct knowledge that a person might display as raw materials for piecing together fuller knowledge than I used to. Hopefully, I'll be able to be a more efficient, effective, and maybe even more enjoyable teacher as a result of this. Thank you for joining me for this presentation. I'd really appreciate your input. Please take note that you can find more of my academic work on my research page on my website, www.learnscience.coza.